And so just some examples here, you see these A and D would be perfect correlations, perfect positive, perfect negative. B and E would be strong. Notice all those points are pretty close to each other. C and F would be moderate. Those points, they do go up or down, but they're not that close to each other. This is what we're talking about here with R. R would be close to zero in both of these last two plots. But notice that plot G, you could probably say there's no relationship, but in plot H, you would say there absolutely is a relationship. I would call that relationship negative quadratic. And maybe you couldn't come up with those words, but you would absolutely say there's a relationship there. However, there is no linear relationship there, which should make sense when you look at that. There isn't a straight line that you can fit that would connect those points. There's not a linear relationship. It's quadratic. But R only measures the linear correlation. So you have to keep that in mind in that the picture is sometimes as helpful as the value of R, because if I were just given R is close to zero, I don't know if I'm in G or H. So if I have R close to zero, what can I say? I can say that there is no linear relationship. I cannot say there is no relationship. Maybe it is, maybe it isn't. It goes back to, again, there's a lot happening in this chapter with regards to know what you can say and know what you can't say. That might be your key to success in keeping all of this stuff straight. If R equals zero, there's no linear relationship. I can say that. If R is close to zero, is there no relationship? Maybe, maybe not. We don't actually know. So some common errors involving correlation. The first one, R is not robust. Remember that word robust means some slight deviations won't affect it much. R is not that way at all. So we need to look at the scatter plot. So the way I like to think about this is we want to use the I-test, but we also want to use the number test as well. The number test is R. What's the value of R? But we also want to look at the scatter plot if one is available. And just like we talked about on the previous one, with the no relationship, no linear relationship, it's a similar idea here, except that there are times when an outlier or two might bring R down, but the picture, you would say, no, no, that's a good relationship. There's just an outlier that's messing with it. Okay, so again, make sure, remember that word robust. We talked about that in chapter 2, right? Robust means an outlier or two is not going to affect it. That does not apply to R. So if I can give you the value of R of a situation and say it's 0.3, and you'd say, oh, that's not very good at all. That's pretty weak. But I might give you a picture of points that are pretty correlated that look like they have a nice, good relationship, but an outlier or two could really affect that value of R. Next, positive correlations imply positive slopes, but large correlations do not imply large slopes. Put a star by this one. This is one of the most commonly missed questions on the exam over this chapter. This is something that you have to figure out how to wrap your brain around, whether it's uh, just reading the same statement over and over again, seeing some examples, whether it's flashcards. You get a couple of different options, but make sure you understand what we're saying here. If I have a positive slope or a positive correlation, I know that the other one is also positive. And the same holds for negative, right? If I have a negative correlation, that tells me I have a negative slope. If I have a negative slope, that tells me I have a negative correlation. That doesn't work with the number, though, with the magnitude. Slope is rise over run. So if my slope is negative, that means I'm falling as my x gets bigger, and that's what a negative correlation literally means. But if I have a large slope, that doesn't tell me I have a large correlation. If I have a large correlation, that doesn't tell me if I have a large slope. They mean two different things. You have to understand that the number of the correlation tells me nothing about the number of the slope. The slope tells me what the tilt of the line is. Right? A slope of 20 means my line is tilted very far up. A slope of 1/2 means my tilt is very flat. Correlation tells you nothing about the tilt. Correlation tells you how close the points are together. Look at the top of the page. The value of R gets bigger or smaller based on other points close together. It has nothing to do with the tilt. That's what slope is. So you have to understand that correlation's this neat thing because there's two pieces to it. The sign tells you the direction and the number tells you how close the points are. Slope works very similarly. The sign tells you the direction, but the number tells you the tilt. Okay, so make sure we catch that the slope and the correlation, the signs have to agree. The signs both tell you the same thing. The numbers tell you different things. And that's what I mean by large, the magnitude, right? A correlation of 0.9 doesn't mean I have a large slope. Maybe, maybe not. Correlation of 0.2 doesn't tell me I have a small slope. Maybe, maybe not, right? The number on the correlation tells you how close the points are together. The number on the slope tells you the tilt of the line, two different things. So the signs have to agree. The numbers may or may not agree. Again, what do you know? What do you not know? What can you say? What can you not say? Next one here, averaging data may suppress individual variation and inflate R. That's not necessarily a good thing or a bad thing. It's just something to make sure you're aware of, that anytime you have data that you're plotting and it's aggregated data, whether it's sums or averages, because an average is just a sum divided by n, right? You're going to suppress individual variability, which can make R look higher. And if you are interested in that, that's fine. But if you're not, then make sure that's not the data that you collect. It's the idea of this. If I were to plot out store size as my X variable and profit as my Y variable, I would say there's a relationship there between the size of the store and its profit, but there are more variables than that. So that wouldn't be the strongest correlation, because a small store that sells, you know, high-tech equipment, cell phones, things that are small that are valuable, would probably have a higher profit than a large store that might sell things that don't have quite as high margins, right? So it would be a positive relationship, but it wouldn't be super, super strong. But if I took averages of the average store size in a city and profit, now all of a sudden I'm going to get a nice, pretty, relationship that's very strong, because the averages are going to take away that variability that we have of some small stores don't make as much money and some small stores do, right? There's that variability there that exists. And that variability, again, it isn't good or bad. It just is what it is, right? So it depends on, am I trying to make an inference on the average store size, or am I trying to make an inference on an individual store? So it just goes down to making sure you're careful with what data you have. Anytime my data is averages or sums, I can only make, like we've always talked about, I can only make inference on that data. I can only make inferences on averages or sums, and that may be what you want, and it may not be what you want. So just going back to what we've long said, we want to make sure that our data is representative of what we're trying to make an inference on. If we want to make inferences on that, great. Use the averages or the sums. If we don't, then make sure you don't have that, because it's going to fall apart here just like it's been falling apart all course if we don't have a representative sample. We've touched on this. The lack of a linear relationship does not imply a lack of a relationship in general, right? Anytime R is 0 or close to 0, you say there's no linear relationship. Maybe there also is no relationship overall. Maybe there is a relationship that's just of a different form. Who knows? You would need the picture in order to determine that. And the last thing, just one more time, correlation does not imply causation. Most important thing from this chapter, to make sure you understand, it does not mean that two rules are correlated. Does not mean that one caused the other. It doesn't mean that one didn't. It just means it doesn't mean that it did. Okay, and just to hammer this home, ice cream consumption has a positive correlation with drowning rates. We know this. But does eating ice cream cause drowning? Say no, that's ridiculous. Eating ice cream does not cause drowning, but it is related with it. Why is that? Because people eat more ice cream in the summer. And yes, you may say I eat ice cream in the winter, but a lot of people don't, right? There is more ice cream consumed in the summer. And guess what? There's more people who swim in the summer. There's more people who drown in the summer. Okay, so as ice cream consumption, if I just pick any random day, I can tell you a better estimate of how many people are going to drown that day based off how many people are eating ice cream that day. The more people that are eating ice cream, the more people are going to drown. The fewer people eating ice cream, the fewer people are going to drown. That does not mean one caused the other, right? In this case, there's what we call lurking variable. That lurking variable is temperature, right? When it's hotter outside, people eat more ice cream and they go swimming more. That doesn't mean it caused it. Now, there are many examples that you'll see where the two variables are correlated and one does cause the other one, right? It's just going to show again, it doesn't imply that, it doesn't mean that. Two variables are correlated. Maybe there's causation, maybe there isn't. We just don't know. In some cases, it's very clear that there is. In some cases, it's very clear that there isn't. In some cases, it's not clear at all. In some cases, you think it might be clear and it's not. And that's where we have to be careful that we sometimes try to jump to conclusions, try to say, this is clear, this one caused this, this other thing. And maybe that's true and maybe it isn't. So we have to be very careful. And so for any situation going forward in this course, what I want to make sure you understand is that two variables are correlated. I want you to always say to yourself, maybe it caused it, maybe it didn't. We don't know. Okay, that's what I need you to take away from me yelling correlation does not imply causation at you multiple times here. How do we interpret R? We've talked about that R is a value that goes from -1 to 1. The closer it is to 0, the weaker it is. The closer to 1 or -1 it is, the stronger it is. How do we actually interpret it? Here's some rule of thumbs. There are other rule of thumbs out there. There is no one method that's perfect. This is just what I'm using. If you use a slightly different one, it's okay. The examples that you will see are ones that, for the exams, for the homework questions, are ones that are not meant to trick you. They're not meant to try to be on these fine line, borderline cases. It's just, you get the general idea. And if you use these rule of thumbs or something slightly different, that's okay. If the absolute value of R is less than 0.25, so if R is between -0.25 and 0.25, again, close to 0, then we say no. Linear correlation, and key, you have to add the word linear, right? Because there might be a correlation, there might be a relationship. It's just that that relationship is not linear if R is that small. If the absolute value of R is between 0.25 and 0.5, and again, notice here I'm talking about absolute value of R because, as I said, it will probably help you to think of the sign of R, whether it's negative or positive, as its own entity and divorce that sign from the number. Okay, so if that number for R is between 0.25 and 0.5, we're going to conclude a weak linear correlation, and we're going to tack on the word positive or negative based off what that sign was. If R is between 0.5 and 0.75, we're going to call that moderate. And if you're larger than that, again in the 0.8, 0.9 range, we're going to say strong.